Good morning. Today we shall begin our study on the topic of concurrency. Now, concurrent execution of programs is a necessary criteria to increase the throughput. We know from our studies of operating systems that whenever we have a single program executing on the computer, then due to a lot of I/O operations on a program, the CPU effort is not utilized. In order to increase the utilization of CPU, we have the concept of multiprogramming. Multiprogramming is a mechanism by which more than one memory resident programs are in an active state. So, more in terms of database terminology, we shall say that more than one transaction is in an active state at a point of time. This means that instead of running the transactions one after another in a sequential fashion, we can have several transactions running simultaneously. If we have more than one processors, then this situation can be visualized very easily, in the sense that there is one transaction running on one processor, but due to the commonality of disk, they may access the same disk. Even in the case of a single processor, so we can have multiprocessing, which is a very common way of having multiprogramming, or we can have on a single processor, we can have multiprogramming in what is called a time shared fashion. In a time shared processing scheme, each transaction is given a certain slot of time for execution, and after that this transaction moves on to a suspend state, and another transaction is given the time slot for occupying the central processing unit, and this way it goes on in a round robin fashion, so that processors all among the active transactions, the CPU time is equitably distributed or distributed according to a certain criteria, so that the processing can be done on each and every transaction. Those processors which require I/O access are separately accessing the I/O processor and do not utilize the CPU time. This way, even in the case of a single processor, using time shared mode, the CPU utilization is better and the throughput is increased. These two are standard OS terminologies, and concurrency is a very effective means of solving problems on the computer. In the database technology, we see that in a railway reservation system or in any other systems where there are multiple terminals and multiple users, all of them are going to simultaneously access a database. Now, what are the issues or what are the advantages of doing so is obvious, but in order to maintain the consistency of the database, we have to take care and we have to protect the database from being corrupted, in the sense that more than one processors may simultaneously access some data and may change the consistency. So, we first have to see how consistency can be broken down due to multiprogramming, and then we will see what are the mechanisms to avoid that and yet maintain the multiprogramming advantages of multiprogramming. So, The first issue is that of if we have got two transactions T1 and T2 and they access totally different pieces of data, they do not access the same data, then there is no problem in executing them concurrently. It does not matter which one goes before which one goes after which one. It does not even matter whether if they are interleaved, that is half of T1 is executed, then T2 starts, 1/4 of T2 is executed, then the rest of T1 is executed, and then the rest of T2 is executed. If T1 and T2 do not share any piece of information or data, then there is no difficulty at all. The difficulty comes up when T1 and T2 do share some amount of information. And let us see what is the problem when T1 and T2 do share some amount of information. So, the problem of inconsistency may arise only when we have got shared data. In order to study atomicity and inconsistency or consistency, we have to see what is meant by concurrent execution of more than one transaction. Now, let us understand that T1 and T2 can be executed concurrently means what? It means that even whether they share data or they do not share data, if T1 executes before T2 or T2 executes before T1, that is, we have T1 followed by T2 or T2 followed by T1, both of them must be valid. They are concurrent in the sense that the first criteria of two transactions can be concurrent, that they can be executed concurrently, is that if T1 follows T2 or T2 follows T1, there should be no difficulty. What is the example of this? In a railway reservation system, when you are booking, cancelling, 5 or 6 people are doing it. The transaction for booking, the transaction for cancelling, all these transactions at each individual terminal are concurrent. It does not matter if one transaction goes after another or another transaction goes before another. So, this one is also a correct execution, this one is also a correct execution of both of the transactions. So, that must be understood very clearly when we say that two transactions are potentially concurrent. T1 followed by T2 or T2 followed by T1, both are correct. And some of their interleavings is also correct. For example, if they do not share any data, then any sort of interleaving is okay. But if they do share data, we will see that all sorts of interleavings are not okay. So, a schedule of more than one transactions is the exact sequence in which the portions of each transactions are executed. For example, if T1 and T2, if T1 follows T2 or T2 follows T1, then we say these are called serial schedules, schedules which one distinctly follows another. A schedule is said to be concurrent if they interleave, that is, a portion of T1 is executed, then a portion of T2, then a portion of T1, then a portion of T2, and this concurrent schedule may be there for not only two but for more than two transactions. And a schedule is the exact sequence in which the transactions occur. Let us take two examples of two transactions. The first one is read x. This is actually read, as we have said before. This is a disk variable. It will actually, this is corresponds to read x comma small x, and this is actually small x is assigned small x minus 100. This is done on the memory. These are memory variables, and these are disk variables. and as we have studied before, it should actually be read x comma x this is like this, but since we are doing it often and just to avoid writing it out so many times, by default when we write this we mean this, when we write this we mean this. So this is a schedule, this is a transaction which deducts 100 from a particular variable and adds 100 to another variable and writes out these two values back into the disk. This deducts 20% from a particular variable and adds that amount to another variable. So in terms of a bank transaction, this deducts 100 rupees and adds 100 rupees, that this does a transfer of 100 rupees from x to y, and this does a transfer of 20% of x to y. Now these are two transactions and they share two variables x and y. Now it does not matter to us whether T1 runs before T2 or T2 runs before T1. Both of them are correct and consistent. It just means that after T1 the value of x plus y must be same as before it executed, and after T2 the value of x plus y may be before it is executed. And T1 and T2 can be interleaved in any fashion, but the value of x plus y must be consistent. That is the consistency criteria. So if they are executed serially, then if T1 follows T2, so that is if we have a serial schedule T1 followed by T2, or if we have another serial schedule T2 followed by T1, both of them are consistent schedules. Now let us see an interleaved schedule. This is a schedule where we have tried to specify on each row, this is step actual time step 1, time step 2, time step 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We are as if running it on a single computer. If we ran it on a multiprocessor, then the situation would be slightly different, but that is at the same instance of time we would have more than one execution, but that would be valid only for these operations. But for the write operation, you just, if you write both of them simultaneously, then we have to know what is meant by that concurrent write on a particular disk. So we are now considering what we do on a single processor, and these ideas will carry automatically what we do on a multiple processor. So first we have these three statements executed of transaction T1, then the transfer of control goes to T2, which executes these 4, then the transfer of control comes back to T1, which executes these 3, and then the transfer of control comes back to T2, which executes these 3. Let us remember that these x and t are memory variables, and only the read and write operations actually access the disk. It may be buffered, but whatever, that the disk management system or the operating system will take care of what is happening. Now, is this interleaving schedule consistent with our consistency criteria? Let us see. Let us start with x equal to 500 and y equal to 1000. Then at this point of time, after the write operation is done, by the way, I would just like to mention here that we are not considering failure at this particular point of time. We are assuming that there is no failure. Just we are discussing the issues relating out of concurrency. So at this particular point of time, x will be 400 and y will be 1000. At this particular point of time, x will be 400 minus 80, 320, and y will be 1000. At this particular point of time, x will be 320 and y will be 1100. And at this particular point of time, x will be 320 and y will be here 100 is deducted from x, here 80 is deducted from x, here 100 is added onto y, and here 80 is added onto y. So after this concurrent execution of these two transactions, we still have x plus y is equal to the original value, that is 1500. And if you take any initial value of x and y which is available, obviously these are positive and obviously these are greater than 100, both of them, at least x is greater than 100, we will see that for any value of x and y the consistency is maintained. It is not difficult to prove that the consistency is bound to be maintained. So this is a consistent schedule. More so, we will see that a schedule this is not only consistent, this is equivalent to a serial schedule. The final result may depend on the order in which they execute. That is not our problem. Look, two transactions are concurrent. It is to be understood very clearly that the final result will depend on the order in the schedule, the manner in which the schedule is executed. The final result, even if they are executed sequentially, if T1 executes before T2 or T2 executes before T1, the final result will vary. And that is not wrong, that is correct. You go to a railway reservation counter, if someone books the ticket before you, or see if two people are booking a ticket, and whoever books the ticket first will have a particular seat, whoever books the ticket second will get another seat. If the second person got the chance earlier, then the result would have been different. So it is not incorrect. These two transactions are both correct.
On 31st of a month, a person deposits 100 rupees in a particular account and withdraws 100 rupees from it. And on that particular date, the bank calculates the interest from both the accounts and gives it there. This would give different interest values.
These two are not concurrent schedules at all. These two are not concurrently executable schedules at all. When we talk of schedules which are concurrently executable, we mean that, see, suppose a bank says that on the 31st of the month, whatever is your balance, I will give you 20%, like this is done here. Then that means that the bank will consistently do it at the end of the day, when no other transaction takes place. But if the bank says that I will do it at 10 o'clock, then bank will obviously make sure that no other transaction takes place at 10 o'clock. That transaction will not be concurrently executable with anything else. Here we have taken an example in which one person, like for example, say it's an IIT account, and somebody says there is an order, deduct 10% from the bank account just now, and another gives transfer 100 rupees from here to there, and somebody says transfer 20% from here to there. And if it is allowed to be concurrently schedulable, then these two are allowed. Then it does not matter which one. But if the whole operation is such that it cannot be, if T1 followed by T2 is correct and T2 followed by T1 is not correct, then obviously T1 followed by T2 must be done. They are not even, there is no question of concurrency out there.
How do you define define transactions which are concurrent?
You define transactions which are concurrent by saying that these two are concurrent. There are so many transactions which can be concurrent. Go to a railway reservation system, all transactions are concurrent. There is no problem in having a concurrent transaction out there. So we are assuming that these two transactions are defined to be concurrent a priori. This matter should be understood very clearly. That even if T1 followed by T2 and T2 followed by T1 gives different results, and they are defined to be syntactically that they are concurrent. They are defined by the developer that these two transactions can be executed concurrently. Then it should not matter whether T1 is executed after T2 or T2 is executed after T1. So we are assuming that these two transactions are defined to be concurrently executable. Now among these, but there is a consistency criteria. The consistency criteria says that when two transactions are executed concurrently, then x plus y should remain same. That is the consistency criteria of each of them. Whatever be the result, I don't care, but this consistency criteria must be maintained. Now let us see this example. In this example, the consistency criteria is not only maintained, the result which we get is equivalent to a particular schedule. It is, if this is T1 and this is T2, then the result of executing this is equivalent to executing T1 followed by T2. So now we come to the exact result, exact output. And the output that you get here is equivalent to executing T1 followed by T2. It is not the same as executing T2 followed by T1. On the other hand, if this part was done first, this part was done second, this part was done third, and this part was done fourth, that would also be a concurrent schedule equivalent to T2 followed by T1. Now let us see another one. Let us see another concurrent schedule. In time step 1, this one is done. In the first block, this one is done, then this one is done, then this one is done, then this one is done. This is equivalent to T2 followed by T1. So all these are not only concurrent schedules, but they are called serializable schedules, in the sense that they are equivalent to a serial schedule. Their result is equivalent to a serial schedule. So such schedules are called concurrent serializable schedules. Let us see another example. Let us see another example. What does this example do? X is equal to 500, y is equal to 1000 initially. So this is time step 1, this is first slot, then T2 does this in the next slot, then T1 does this in the next slot, then T2 does this in the next slot, then T1 does this in the next slot. So at this point we still have x equal to 500 and y equal to 1000. At this point we have x is equal to 20%, so the x becomes 400 and y is 1000. Now what value of x is written here? Here this is x comma small x. So when you write down x here, then you again write down 400. Please remember, this x was read to be 500, this x became 400. This is a memory variable which is like this, and when you write this, this is x comma x, so this x was written into this x, so 400 was written because this was 400. And what y is read out here? 1000. Excuse me. Now what is the x which is read out here? Excuse me. Here both of them read 400, and here x is still 400 and y is 1100. I hope this is okay. Here x becomes 500 and y x is still 400, sorry, and y is 1200. Now this data is not consistent. This data has become inconsistent. Now once this happens, this is a schedule which is incorrect. This schedule is not correct. So this schedule is not a serializable schedule. Firstly, it is not equivalent to any serializable schedule, nor is it consistent with anything. Let us see another example. Let us see two transactions. One is this full thing, x is assigned x minus 100, y is assigned y plus 100. X is assigned y is assigned y minus 60, x is assigned x plus 60. And the consistency criteria is x plus 5. So this is T1 and this is T2. If T1 is first executed, say initially x is 500 and y is 1000. If T1 is executed and then T2 is executed, what do we get? So T1 followed by T2 will give x equal to 460 and y equal to 1140. 1000, this is C, 100 will be deducted and 100 will be incremented and 60 will be deducted, so 1040. This is the result. If T2 follows T1, what will be the result? Same. When it is executed like this, it is also same. So there can be transactions which one is executed after another in any form, it will be identical. We will come back to this example a little later and see what is our criteria, what are the interesting features about this transaction. Even though they share the same variables, in the previous one, since a percentage was taken, the data was different because of their concurrent execution. But here, since just addition is done, there is no difference in their concurrent execution. On the other hand, this is a schedule which is not only equivalent to any, it is not equivalent to any serializable schedule. In fact, it is not a proper schedule at all. It is not a consistent schedule at all. And if A plus B is not our consistency criteria, we say anything can happen, I just don't care. I don't care about the result. There is no consistency criteria. Then this is a correct schedule. But it is still not equivalent to any serial schedule. It is still not equivalent to any serial schedule. Is that understood? So we now come to the question of what is meant by our, how will we study what is a concurrent schedule, which concurrent schedule is correct without executing it. That is, when we schedule it, when the scheduler schedules, gives the time slots and a transaction is being done, how will we understand that this transaction is being done correctly or not? Either we execute the transaction and then say, no, I see the consistency criteria has failed, so we run them all over again. That is quite futile and it will waste so much of CPU time that there is no point doing it at all. You will just run schedule after schedule, because see, if there are two, then there can be how many schedules? If one has got n statements and another has got m statements, you can imagine the number of interleavings that can occur. And based on these interleavings, you can have so many possible schedules, of which 90% of them will be incorrect and inconsistent. So if you try to run them and then check the consistency criteria, then you are in deep trouble. You will not only waste all your CPU time, it would have been better to run them one after another. The whole concept of multiprogramming and multiprocessing will be lost. So we have to devise some schemes so that we are able to prevent an invalid schedule from being generated, and even if they are generated, we have to detect it early and do it as quickly as possible and get a recovery procedure. Recovery in the sense of rollback, that is, we have to prevent these schedules and restart them. So how will we do them? What are the mechanisms for doing them is what is called, is the topic of concurrency control. So that is the topic we shall study. We'll stop and we'll start off the detailed examples next.